Okay, so this is now Unit 7, again, only for separate science, so it is on seismic waves. Again, another quite short unit, so only 3 objectives here. 1, we're going to describe the properties of the different types of seismic waves. We're going to look at simplified seismic records or seismograms to identify the location of earthquakes. And then we're going to use the path of seismic waves to explain the structure of the Earth. Okay, some different video links here just to help us through with a variety of things on seismic waves and how to find the epicenter of an earthquake, which I'm going to do in this video, but again it's just another way of doing it available here. So what are seismic waves? Well, the surface of the Earth is made of plates called tectonic plates. You may well have studied this in chemistry already. If you've done, I think it's topic 5 on Wegener or ever-changing Earth. As these plates move around, they rub on each other. And the movement of these plates then is going to cause waves. So basically when they rub on each other, they cause ripples or waves through the plates, cause an earthquake. Okay, now we have 3 varieties of seismic waves that we need to study for this course. Alright, and they're in this table. So we have P waves or primary waves. They are longitudinal, they're the fastest, which means they arrive first at a location, and they can travel through solids and liquids. Secondary waves are transverse, and they travel slower, and they can only travel through solids. And then we have surface waves, which are a mixture of transverse and longitudinal. They're the slowest of the waves, and they only travel along the surface of the Earth. Okay, seismograms or seismographs. These show the movement of the Earth during an earthquake. Okay, and basically what you have is a big weight or a pen suspended in space, and as the Earth moves underneath it, the pen then draws on the surface, showing how it moves. Now, P waves are always the first to arrive on these. So P waves will always be there first, then S waves, then surface waves. Now, sometimes, because we're not interested in surface waves so much with these, you'll see the surface waves excluded. Okay, now the lag time between P and S waves gives us a clue to how far the earthquake is away from us. Alright, this time difference between when the P waves arrive and when the S waves arrive, okay, that gives us an idea of how far away an earthquake is, because the P wave and the S wave always travel at the same speed, and so as time goes on, the P wave will be getting quicker, well, will reach a point sooner and sooner and sooner compared to the S wave. Okay, so using our seismograms. Now, we always need 3 seismograms to tell us where the centre of an earthquake is. Why is this? Because 3 is the only time that you will get 1 point. Any more than that, any less than that, and you'll either end up with loads of points or 2 points. You definitely need 3. You use your seismograms to calculate the lag time. Then you use a graph of distance and time for P and S waves, and you look for when the lag time is the same time as the time between the P and S waves. That will come clear when we have a look at one. And this is how far the centre of our earthquake is. Do it for all 3 stations. We then use our map and do scale drawing of 3 circles. So if you've done in maths loci, this is talking about loci. Alright, so you draw the loci around these 3 circles. Where they cross, that gives you the epicenter. And like I said, we need 3 because it's our first combination that gives only 1 location. Okay, so here we go. This is us doing it then. Alright, so we have our P waves, we have our S waves. Our x-axis is time. And the other thing you've got a button on your calculator that will look like our symbol here. The degrees, minutes, seconds button. But this can actually be used for time. So you can think of that as hours, minutes, seconds. Alright, so that's quite a useful button to do time on your calculator. Rather than having to convert everything to seconds, you can work in hours, minutes, seconds. Like I said, you then use a graph of the P wave speed against time, the P wave distance against time and the S wave distance against time, and you look for when the gap between those 2 is the same as your lag time, and that will give you your distance. Okay, so here is the scale drawing then. So in my previous example, I'd worked out how far these three were away, and I put a cross where they, where those three circles cross. That tells me where the epicenter is. Again, if you watch the video that's on the useful links, he goes through this in a lot more detail there to help out with this. Okay, so the structure of the Earth. Well, we can use the paths of seismic waves to make assumptions about the structure of our Earth. Alright, we can measure where the Earths go through, and they look like they curve. Now they curve due to refraction. They curve due to the density of the Earth gradually increasing the further down you go. They're speeding up, and it's shown because they're bending away from the normal. Now you might think, Alan, we spoke about density if it's in high density or slow. Remember, these are mechanical waves, so the closer the particles are together, the faster they're going to move. And we see sudden changes in direction, and that shows a sudden change in density. And using all these facts, we come to understand the structure of the Earth. That we have a thin solid crust going around the outside. So a thin solid crust going around the outside. We then have a semi-molten mantle, which we can think of as being solid, and we'll get to how we know that in a minute. We then have a liquid outer core and a solid inner core. Now, if you look at these two, if we start with the P waves, you can see that we get P waves all the way from our epicenter round to a point here, and then all the way again down here, and then around here. We get two P wave shadows. And this is due to the change in density between the mantle and the outer core, between the solid mantle and the liquid outer core. Alright, here our waves will be going from a region, you can see they actually refract the other way. That's because they slow down quite a lot when they hit the outer core. Alright, and so what that means is we get an area here where they just can't get into. Now our S waves, we have a big region all the way around here that our S waves can't reach. And that's because S waves can't go through the liquid outer core. Alright, so that's something to remember. Okay, now over to you again. So, link in the description to the questions, or stop the PowerPoint slides and you can click on this document to have a go. Okay, so welcome to this video going through the seismic wave questions, like we've done on the ones before. Okay, so earthquake monitoring stations can detect P and S waves. Seismic trace contains information about the arrival time of each wave type. Diagram shows the path taken by the seismic waves travelling from X. 3 seismic stations. So compare the traces obtained from A, B and C, explaining any similarities and any differences. Now, they've said about P and S waves, so we don't need to talk about surface waves in this. Okay, so if we look at this, then both A and B are going to get both S and P waves. Probably should put that the other way around, P and S waves. Yeah, we're going to get them both because we're only going through the mantle there. C will show only P waves because remember S can't get through the liquid outer core. Show. Okay, so there we are. Right. Similarities. Well, they're all going to show the same shape of waves. Because they're all going to be showing the same waves arriving. However, what we're going to see is we will see that A has shortest PS lag. Or shorter, let's try it. A has the shorter PS lag, or has shorter PS lag than B, and then at C waves take longest time to reach. So in terms of similarity, we're all going to see the same shape. A and B will see both P and S waves. C will only show P waves. Just says compare, doesn't say explain, so that's fine. A will have the shortest PS lifetime because it's the closest to X. And C will take the longest because it's the furthest away. So hopefully that will make sense for that question. Okay, S waves are transverse waves, P are longitudinal. Describe the differences. So remember, in our transverse wave, our vibrations are parallel to energy transfer. In a no, that's longitudinal, isn't it? Sorry. Longitudinal. So in a longitudinal wave, vibrations are parallel. In a transverse wave, they are perpendicular. No need to write out the whole thing again, that'll do. Transverse wave, they are perpendicular. We're implying from the previous statement, we're talking about vibrations and energy transfer. Okay, so the epicenter of an earthquake is directly above the earthquake. Seismic stations detect earthquakes by tracings made on seismographs. 3 types of P and S waves, surface, 3 types of waves, correct statement. Surface waves travel the fastest, no, they travel the slowest. S waves travel on the surface, no, surface waves travel on the surface. S waves are transverse waves. Yes, we've just said that in the we've just read that in the previous question, so we'll tick that box. P waves travel through solids and liquids, we've just spoke about that, so we'll tick that box. P waves are longitudinal. Yes. P for push, so we'll tick that box. S waves cause the most damage. No, surface waves cause more damage. So we're going to tick those 3 boxes like so. Okay, so we've got a graph showing P and S wave, the time at certain distances. One small square represents 20 seconds on the time axis. Now, why 20 seconds? Remember, time is base 60, so we have 60 minutes, or 60 seconds in a minute, so splitting it up into 3 like this into 20 seconds makes a lot of sense. So you're going to state the time it takes for P wave to travel 5 times 10 to the 3 kilometers. So what we're going to do, we're going to come up from 5, and then we're going to go across until we reach the first one, and we are going to write then, in the wrong box, we are going to write 8 minutes, because it's going to take us 8 minutes, and it's the first 8 minutes, would help if I could read here. It's not going to take us 8 minutes at all, it's going to take us 5, no it is 8 minutes. This is why you need to draw the lines, because I'm doing this before I have the lines, and no, I was right, so it's 8 minutes. It's on the first of them, 20 seconds. Now we want the extra time the S wave takes. So the S wave is going to take, coming up from 5, the S wave is going to take 15 minutes. So we now need to do 15 minutes, take away 8 minutes, 20 seconds. Now the way we can do that is on our calculator. For those of you who can see my calculator, this button here is the one I'm on about for doing time. So we have 0 hours, 8 minutes and 20 seconds. Alright, and we've also got 0 hours, 15 minutes and 0 seconds. And we take one away from the other. I don't know how well you can see that. There we go. So that's the sum we're going to do. And that's going to tell us that our extra time is 6 minutes 40. Okay, so we now got our 3 seismograph tracings made at 3 separate stations. Balboa Heights, Boulder, Colorado, and Mexico City. And we're going to use the information from the graph and the tracings to complete this table. Okay, so we're looking at Boulder, Colorado. And Boulder, Colorado, the P waves arrive. So we on our Boulder, Colorado, our P waves arrive. So we have got 15, 16, 17, 18, 19, 20. Yeah, so our P waves are going to arrive at Boulder, Colorado at 16, so 00, 16, 00. And we got our S waves, so we then have our time difference between those two. So we do exactly the same again. 0, 18, press the button after each set of numbers, take away 0, 16, 00. At the end. Okay, so that's then at 2 minutes at 0 to 40, so 2 minutes and 40 seconds. And then we want the distance to the epicenter. So to work out that distance to the epicenter, what we are going to do is we are going to look for when this gap between our P and our S is 2 minutes and 40. Okay, so we look for when it's 2 minutes and 40. So that is going to be, it's 2 minutes and 40. So we know that it's got to be less than 2.2 kilometers. So let's have a look. When our P wave is at 2 minutes and 40, so that's 1 minute and that's 1 minute and 40. We want 2 minutes and 40. So let's have a look. So at 4 seconds, that's then already up here, so we know it's going to be less than that. So 2 minutes and 40. Probably the best way to do that is go, well, 2 minutes and 40 is going to be 8 boxes. So 1, 2, 3, 4, 5, 6, 7, 8. So it's this line here, and that's 1.246 kilometers. So we're going to write in this box 1.6 kilometers. Okay, and then on this question, find the epicenter of the earthquake. What you're going to do is you're going to draw 3 circles to scale, like so. And where they cross, that's where the earthquake is. Okay, so we've now got a different one where they've already drawn the circles on for us. Label the diagram with a cross, the location of the epicenter. The location of the epicenter is where all of them cross. So that is about there, where they all cross. Close enough. Why do we need 3? Well, this is the first, or the lowest amount of stations. To give only one location. Any less than that, if you use 2, we're going to get 2 locations. If you use 1, you get an infinite number of locations that's somewhere on that line. Which one detected the earthquake first? That is C, detected it first, because it's nearest. Or it's got the smaller circle, but it's nearest will do. Okay, the diameter around station A is double the diameter around circle B. The earthquake happened at 1 hour and 15 minutes and 10 seconds in the morning. The following signals were detected at stations A and B. Due to an error in the equipment, the arrival times T1 and T2 for the signals were not recorded at station B. Use the signal information from A, determine the time that the P waves and the S waves arrive at B. Explain how you arrived at your answers. Okay, so A is double the diameter of B, therefore A is twice as far away. If something's twice as far away, the waves are going to take twice as long to get there. So that means that for station A, it's taken 20 seconds or 10 seconds to get there. That means for station B, it's only going to take 5 seconds to get there. Okay, so the first thing when we're going to say explain, twice distance equals twice as long. Okay, that's how we get to our answer. So for P waves, we're still going to have 1 hour. This time, in terms of minutes though, still going to be 15. But it's half the time, so it's only 5 seconds, so 1 5. For S waves then, well, the S waves took an extra 50 seconds to get there. This time they're only going to take an extra 25 seconds. So it's going to be 1, 15, and 15 add 25 is going to be 40, like so. Now, they might be drawn to scales, you might be lucky and just be able to measure it if you're good with scales, but that's the reasoning, that's the best way to do it in terms of just reasoning out. Okay, use diagram below and your knowledge to compare the properties of seismic waves, P and S and surface. Okay, so QWC as it used to be 6 marks, still probably worthwhile thinking, right, 6 points. So we're looking at probably 2 things about each sort of wave. We've got to use information from the diagram as well. So first thing we are going to say is we're going to talk about the types of waves. So P, they are going to be our push waves, so they are longitudinal. Yeah, P waves are longitudinal, they're the fastest, and they travel through solids and liquids. So, using our information from the diagram, can pass through all layers of the Earth. Good start. Alright, we do the same for S. So S are transverse. They are slower than P. Can only travel through solids, so only the mantle. Okay, and then our surface waves, they are the slowest and they travel along crust. There we are, those are our points for our 6 marks. Okay, so by looking at the seismograms from different monitoring stations, we can find out their distances from the epicenter of the earthquake. The signals arriving at 3 stations are named STM1, STN2, STN3. Use the information in the diagram and the graph below to find the distance from the STN2 monitoring station to the epicenter of the earthquake. Describe how you arrive at your answer. Okay, so if we look at this, we're looking at 2. So if we're looking at 2, we're looking at when the S and when the P waves arrive. So the P waves arrive at 2 minutes. The S waves arrive at 5 minutes. So P minus S is 3 minutes. So now using our graph, we come up from 3 minutes. And we go across from 3 minutes to get, this is really tricky, trying to measure this off my screen. So it's the box below 2000, so that off the graph is going to give us a distance of, if I write it somewhere on the right, it's one box below, so 1900 kilometers. Describe how you arrive at your answer. To me, that maths there saying that P right is 2, S right is 5, P minus S is 3, and I've drawn my nice line on my graph below. That's all explains to the examiner how I got to the answer. Okay, so we're going to describe how to determine the position of the epicenter. We're just going over the same things time and time again. There's only so many questions they can ask on this. Show its position on the diagram below. So we know that STM1 is that, we know that STM3 is that. So describe how we're going to draw it. We're going to draw circles on the map to show distance from each STN will do, where they cross equals earthquake. Alright, and now let's do it. So they've already drawn STM1. Now we've got a scale of 1 centimetre to 500 kilometres. So we'll do that, and we'll draw that one. So we'll draw one that is the right size for STN2. We'll draw another one that's the right size for STN3. Where the 3 cross, that is going to be our earthquake. Okay, diagram shows how seismic waves, we've got that. State which seismic waves, if any, are detected between B and C. So between B and C, those waves must go through the liquid outer core. So we are going to get their P waves. And then between C and D, well, that is between those 2 points. If you look, that is where no waves can get, because okay, you could argue surface waves, but it's a long way round. They probably stop by then, but P waves will either go to D or they'll go to C. They can't go in between them. Explain how the Earth's structure affects the path of the seismic wave as it passes from E to A. So we're only talking about that tiny little bit. So the Earth's structure, how is it affected? Well, density of the Earth is changing. In fact, density of Earth is increasing. Speeding wave up, causing refraction. And then we have just before a sudden change in density, slowing the wave down, causing bend in other direction. Yeah, so as we go through the Earth, it's getting denser. As it gets denser, our wave goes quicker, causes it to bend away from the normal. Then just before A, we've got that sudden change in density where the wave slows down because density is decreased and it bends in the other direction. Okay, hopefully that helped. And on to the next one. Okay, thanks for watching this video. Well done for making it through right the way to the end as well. If you liked it, click like. If you got any comments about stuff that's missing, any improvements, anything you didn't understand, leave them in the comments below. If you look around me, there should now be the playlist for all of these videos, along with YouTube's algorithm recommended one of our other videos that you should go and watch. Also, don't forget to subscribe to the channel, follow us on Twitter, link in the description, just to see the other sort of stuff that we produce.